Let's look at some practice buffer problems. So make sure that you have your calculator handy and your Appendix D. All right, so we want to calculate the pH of a buffer that has 0.12 molar in lactic acid. So this is our HX concentration, and 0.11 molar in sodium lactate. So again, this is our salt that 100% dissociates. So we know that this is our lactate, or the X minus concentration. Great, so let's find the Ka of lactic acid. So we're going to look up lactic acid for 1.4 times 10 to the negative 4. So we've got our Ka, 1.4 times 10 to the negative 4. So let's plug this right into the Henderson-Hasselbach equation. Our pH is equal to the negative log of our Ka, 1.4 times 10 to the negative 4, plus the log of our base, which is 0.11, over the concentration of our acid, 0.12. So we just need to do some calculator work here. The negative log of 1.4 times 10 to the negative 4 plus the log of 0.11 divided by, divided by 0.12. We should get a pH of 3.82 units. Now it makes sense if we've got lactic acid in there. All right, let's look at this next one. Calculate the pH of a buffer formed by mixing. Okay, so we're given a volume and a concentration of that lactic acid with a volume and a concentration of the conjugate base. So since we're mixing two different volumes, we need to do our M1V1 equals M2V2 to figure out what the concentration will be when we mix these two volumes together. So let's look at that first. We'll look at the lactic acid. We'll do M1V1 equals M2V2. So the molarity first was 0.13. Volume was 85 milliliters. We don't know what the new concentration is after we mix it, so we're going to say M2, but V2, volume, after I mix them, is 85 plus 95, which, let's just do some, make sure I don't mess it up, 85 plus 95, 180 milliliters. So we just need to divide both sides by 180 milliliters to get our molarity for lactic acid. So 0.13 times 85 divided by 180. So our new molarity is, let's go to 2 sig figs, 0.061. Well, you know what? I'm going to go one more since we'll round at the very end. 0.0614. Okay. So there's our lactic acid. Now let's do it for our sodium lactate. All right, so our M1 is 0.15. V1 is 95 milliliters equals, I got to find my concentration, and then volume is the same volume. One is 180. All right, so divide both sides by 180. So M2 is 0.15 times 95 divided by 180, 0.0792. Okay, there's our concentrations. Now we can plug we've got our acid concentration, we've got our lactate concentration, which is that conjugate base. Now we can plug that into the Henderson-Hasselbach and find the pH. So I'm going to use a different color here. We've got pH is equal to the negative log of the Ka of lactic acid, which we just found up here, are 1.4 times 10 to the negative 4, plus the log of our base, which we said is 0.0792 over our acid, 0.0614. And let's plug this in and see what we get. So negative log of 1.4 times 10 to the negative 4 plus the log of 0.0792 divided by 0.0614. Should get 3.96 pH units. Notice that our pH rose a little bit. If we look, let's see, my acid concentration was definitely smaller. It was about half of the concentration, went from 0.12 to 0.06. And my base was at 0.11 there, and my base went down just a little bit, but my acid concentration was in half. So, all right, let's look at number 3. The pH of this buffer, so we have 5 grams of ammonia and 20 grams of ammonium chloride added to enough water to form 2.5 liters. All right, so hopefully bells are going off and you're like, oh, we can't do anything with grams. Grams, we have to get to moles. So let's do that. We have 5 grams of ammonia, which is NH3. And we should be able to recognize that ammonia is my base. All right, so let's do grams to moles. If I add up nitrogen and 3 hydrogens, I should get 17 grams of NH3 and 1 mole of NH3. So 5 divided by 17, 0.2941. That's moles. And let's go even further. We want moles per liter to get molarity for our base. So let's divide that by 2.5 liters. So divided by 2.5, and we'll get 0.118. Okay, so we have concentration for my ammonia. Let's do the same thing with our 20 grams of ammonium chloride. NH4Cl, ammonium chloride. So this is going to be my conjugate acid, right? Our ammonium chloride is just going to be a spectator ion. So our conjugate acid, with that being my base. So let's figure out molar mass of ammonium chloride. 1 nitrogen, 4 H's, and 1 chlorine should be, 53.5 grams NH4Cl and 1 mole of NH4Cl. So 20 divided by 53.5. And we're going to do the same thing. We're going to take our answer at 0.3738 moles, and we're going to divide that by 2.5 liters. So we can get molarity of that. 0.14, we're going to say 0.150. All right. So now we need to do some plugging into our Henderson-Hasselbach equation. To find the pH, we need the negative log of the pKa, or I'm sorry, I'm going one step too far. pH is equal to the pKa plus the log of our base over our acid. So we know that we were able to do this by the negative log of the Ka, but we don't have the Ka, do we? Because this is NH3, ammonia is a base. And if we look on our Appendix D and we find ammonia, the Kb is 1.8 times 10 to the negative 5. So down here, I'm going to write Kb 1.8 times 10 to the negative 5. I need the Ka. So let's let our calculator do the work. We can find the Ka by doing the constant, the Kw, right, for water is 1 times 10 to the negative 14th divided by Kb will give me my Ka. So the log of, if I do this divided by that, I get Ka. So now let's do plus the log of our base, which is our 0.118, divided by my acid, 0.150. And let's see what we get here. The negative log of 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5. We're going to plus the log of 0.118 divided by 0.150. We get a pH of 9.15. If we think of this, does this make sense? Well, that's a basic pH, and we have our NH3, our ammonia. So yeah, we will have a basic pH. This next one says, write the net ionic equation for the reaction that occurs when a few drops of nitric acid are added to the buffer. So let's think about what our buffer is. Our buffer, right up here, is made up of NH3, which is our base, and NH4 plus, which is our conjugate acid. All right, so this is our buffer solution. So we're adding nitric acid, which is HNO3. So acid is going to react with the base, NH3. Now, we can leave off this nitrate because that's just going to be a spectator ion. And we can just look at the H plus from that acid reacting with our base. So we have this proton donor going to come over here and it's going to create an H4 more acid, the conjugate acid. Remember, if we went back and looked at our diagram from the last notes, we have our buffered system. We're adding a strong acid. So we have our H plus the conjugate base to give us more acid. That's it. The next says, write a complete ionic equation for the reaction that occurs when a few drops of potassium hydroxide are added to the buffer. So if we look at KOH, we know the potassium hydroxide, specifically this OH, this is a strong base. So the potassium, we can leave that off because that's just going to be a spectator ion. We'll cross that off just like we did over here. So we're going to be left with OH minus. OH minus, our base, will react with the conjugate acid from our buffer. So not the NH3, the NH3 base wants to react with the acid, if that's added. The NH4 reacting with, so the base wants to react with the acid. Again, our acid is our proton donor, so it's going, one of our H's will go over here, so we're going to have water, and then we're left with NH3. So we can see that when a base, strong base, is added to the buffer, it's going to react with the conjugate acid to form water and more of the base. And again, if we go back to my diagram, here we have our buffered solution. We're going to add a strong base. So we have hydroxide plus the acid to give us water and more of the conjugate base. This next one says, how many grams of sodium lactate? Well, the first thing that, when I think of grams, I think of moles, right? And when we're doing all of our concentration equations here, we know that we can get to moles if we know molarity. So it's asking us grams of sodium lactate. Now remember, sodium lactate, that's our salt, and our salt 100% dissociates into that conjugate base. So this is asking for that anion, that base. Should be added to 1 liter of 0.15 molar lactic acid, so we know our concentration of our acid, to form a buffer solution with a pH of 4. Assume that no volume changes. Okay, so we know the Henderson-Hasselbach pH is equal to pKa plus a log of B over A. All right, so let's plug in what we know. We know the pH is 4.00 is equal to the negative log of, let's look up lactic acid. We actually did that way up in the problem up there. It's Ka is 1.4 times 10 to the negative 4th plus the log. We don't know what the base is, but we do know the acid is 0.15 molar. Okay, let's do a little bit of simplifying. If I do the negative log of 1.4 times 10 to the negative 4th, I get 3.85. So before I even move on to over here, I want to subtract this from both sides to do a little bit of reduction. So let's subtract 3.85 from both sides. So 4 minus my answer. So I could reduce this right off the bat and get 0.146 is equal to the log of base over 0.15. Now to get rid of log we need to, the opposite of log is 10 to the power of 0.146 will then be equal to base over 0.15. So let's plug that in, 10 to the power of, my answer, we get 1.4. So we can then say 1.4 is equal to base over 0.15. So now we just need to multiply these two together to get B. So B is equal to 1.4 times 0.15. We get 0.21 molar. Now remember, that is moles per liter. All right, so we still got a little bit of work left to do. This 0.21 molar, I'm going to go over here. 0.21 is moles per liter. And we were told that it's in 1 liter, so 0.21 times 1 still gives us 0.21 moles of sodium lactate, which is NaC3H5O3. Now, to get rid of moles and get to grams, we need to find the molar mass. So 1 mole will be on the bottom here. And let's add up our molar mass. We've got sodium, which is 23, plus carbon of 12 times 3, plus 5 hydrogens, plus 16 times 3 for our oxygens, and I got 112 grams per mole. So 0.21 times 112, and I should get 23.52 grams. And let's just make sure we've got 3 sig figs, 2 sig figs it looks like. So we're going to say 24 grams of this sodium lactate.